So we're ready for our third thermodynamic term, which is called Gibbs free energy. We had enthalpy, which was H. We had entropy, which was S. And now we're going to have free energy, otherwise known as Gibbs free energy. And it's abbreviated with a G, okay? It can be used to predict spontaneity. It's not like we're throwing out the second law of thermodynamics, where the delta S of the universe is your predictor, but we're going to see this new thing, which is free energy, and it is a wonderful tool for predicting it, okay? So we're going to derive the equation that we will use from what we already know here on the screen. So for a spontaneous reaction, this was our starting point, right? The delta S of the universe is the delta S of the system plus the delta S of the surroundings. If that is greater than 0, that's spontaneous. That was the second law of thermodynamics. Now, what I'm doing is simply replacing the delta S of the surroundings with what we learned is how we calculate it. Remember that equation. Delta S of the surroundings is equal to negative delta H of the system. That's the reaction divided by its temperature. Now, on the next step, can you look at it and see what happened? A couple things happened. The T's got moved around. They did a little shuffling there. Another really interesting thing is the sign changed, didn't it? So what have I done to go from this step to this step? All I've done is multiplied through by a negative T. Everything got multiplied by a negative T. So the delta S, oops, sorry, there we go. The delta S of the universe got multiplied by a negative T. The delta H, this part right here, got multiplied by a negative T. And that just gave us a positive delta H, which got moved over here. Okay, so it got put over here. And the delta S of the system got multiplied by a negative T. And that gave that to us. And when you multiply an inequality by a negative value, it changes the sign of that inequality. Okay, so we've done some manipulations here, starting with our same second law of thermodynamics equation. Now what we do is take this portion, let me just re-highlight what we're pointing at here. We take this portion and call it the delta G of the system. Okay, the delta H of the system minus the temperature and the delta S of the system will give you delta G of the system as long as you're measuring it at a constant temperature process. Okay, so what this tells me is if it was true that the delta S of the universe is greater than 0, it was spontaneous. This tells me that as long as the delta G of the system, which is what this portion right here is, as long as that is less than 0, then it is going to be spontaneous. So let's rewrite everything that we see here at the top of our next screen. Well, it's almost the same thing. I got rid of the delta. Gibbs free energy, which is just the G, is defined as H minus T times S. Now we can know entropy and have a value for that. We can know temperature and have a value for that, but we cannot know just plain old enthalpy. We can only talk about enthalpy change. And so we can't really have a value just for a G of a system. You know, it's going to have a, you can't say that this thing has this much G, but this is the definition of Gibbs free energy, which is abbreviated with a G. Our working definition at constant temperature looks like this. And this equation is true both not in standard state conditions and in standard state conditions. So I will go ahead and rewrite it. If everything is 1 atmosphere, then we can use this to obtain our values for, and we can monitor it with standard state conditions. This is an equation that you need to commit to memory. Delta G equals delta H minus T delta S. Now we're going to just really examine this equation in a lot of detail. So I'm going to rewrite it up here. Delta G equals delta H minus T delta S. This is delta H of the system. The reaction taking place is changing its enthalpy. This is delta S of the system. It is changing its entropy. It's either getting more or less disorder. Of course, this is the temperature. And this is delta G of the system. So we're now able to talk about the system and not even focus on the surroundings by using this equation. Now, why is it called free energy? When a reaction gives off heat, that heat can do work, but not all of it can do something. Some of it has to be reserved for another reason, and we'll talk about that other reason as we go. So it is the portion of this that is free and available to do work, and that's why it's called Gibbs free energy. Just because something gives off 5,000 kilojoules doesn't mean you can use all 5,000 kilojoules to do a process, to do something else, to heat a home or what have you. It might give off all that energy, but only some of it is free to do what you want it to do, and that's where it gets its name as free energy or Gibbs free energy. So we have a table which is a summary of the sign convention. It's the opposite sign convention of what the delta S of the universe was. The delta G, if it's small, if it's less than 0, if it's negative, in other words, that's when you've got a reaction that's spontaneous as written. In the forward direction, from reactants to products, it is spontaneous. If delta G is greater than 0, we would say the reverse process is spontaneous. We don't say it's not spontaneous. It's more than just not being spontaneous. We know that if it went backwards, if it went in the reverse direction, it would occur spontaneously. Okay? And if it is equal to 0, then it is a process that's at equilibrium. Now, we're not going to talk a lot about equilibrium right now. Eventually, you're going to have a couple chapters where we're going to talk about equilibrium, really study equilibrium, and we'll come back to this notion of delta G being equal to 0 and being at equilibrium. But you can have a process at equilibrium, and right now I'll just tell you what that means. The forward reaction and the reverse reaction are both occurring at exactly the same rate. And so the forward reaction is occurring and the reverse reaction is occurring. If they're happening at the same rate, it's at equilibrium, and when that happens, the delta G is 0. You're getting some energy out, putting it back in for both of those processes. So here's a table. I'm going to construct this table underneath what we see here. Okay? So I have got the sign of each of these things. Okay? Now temperature is always positive. Why is temperature always positive? Well, temperature is in Kelvin. And there's no such thing as a negative Kelvin, is there? So we're going to go through these possible scenarios here and think about the sign of these and how that's going to affect the sign of delta G. And I've got 4 scenarios, 1, 2, 3, 4 scenarios as we fill in this table. Now, the first situation is this. I told you that more reactions are spontaneous when they're exothermic. So there's my exothermic process. And more reactions are spontaneous when delta S, when you have an increase in disorder. That is not a perfect predictor. That is not a perfect predictor. But I want to know if this was negative, and this is positive, and this is positive, and you're subtracting it from there, I want to know what's going to be the sign of delta G. Okay, that's going to be your first question. Delta H is negative. Delta S is positive. Now T is definitely positive also. I'm subtracting this term from this negative number. What is true? Is delta G always negative, always positive, or it might be positive, it might be negative, depending upon the size of the temperature? Well, hopefully you came up with that it is always negative. If you think about a number line and you're starting at the negative end and you're subtracting a number from it, you're getting more and more negative. So delta G in this situation will be always negative. What do we know about the spontaneity? If it's delta G is negative, now you might have to flip back in your notes. But if delta G is negative for a reaction, can we predict if a reaction is spontaneous? Yes, it is always. I don't know why I wrote a D. That was supposed to be an A and an L. Let's try that again. Always spontaneous. Okay, always spontaneous. So the two conditions that I say you're going to see more often than not on a spontaneous process, it's exothermic and getting more disordered. If you've got those two things going for it, that reaction is going to be always spontaneous at every imaginable temperature. Okay, so that is that one. All right, let's keep going with this table and let's consider the other possibilities. I'm going to just for the heck of it, put that back there. All right, second scenario is reverse it. Let's make this positive and this negative. So we're starting with a positive number. We're subtracting these two, where if this is positive and this is negative, we're subtracting a negative number. Well, if you're starting with a positive and you're subtracting a negative number, what is subtracting a negative number the same as? It's the same as adding. So you're starting as a positive and adding to it. So delta G would always be positive. Always positive. Always spontaneous in the reverse direction for that reaction. Okay? This is an unfavorable condition matched with another unfavorable condition. You put those two together, you will not have a spontaneous process as it's written. It will be spontaneous in the reverse direction. All right, that's two possibilities of the four. What if they're both positive? All right. So this is positive, and we're going to subtract from it. I want to know what conditions will make it spontaneous. What will make this negative? Okay, it's not negative always. Okay, so I'll put it in parentheses. What will make it negative? If we start out as a positive number and we want it to be negative, this term has got to grow big enough, okay, so that when we subtract it away, it ends up being negative. Now, we can't change this number. It's a positive value. It's something. But we can change the temperature. What kind of temperatures are going to make the reaction spontaneous? So it's going to be spontaneous at high temperatures. You might need to stop and think about that. Do you get what I'm saying? We start out with a positive number. We're going to subtract a positive number from it. You subtract a big thing from something that's got a value. Eventually, if it gets big enough, you're going to be a negative number. So some high temperature will become spontaneous, and every temperature above that, it will also be spontaneous. Baking a cake would probably be an example of that. You stick it on the counter, it does not bake. You raise the temperature, it will bake spontaneously. High temperature bakes cakes, okay? So that would be a situation of that. All right, how about negative and negative? Again, there's not an always, but what kind of conditions can get to me a negative value of delta G? Sometimes this would be negative, sometimes this would be positive. I want to know what will make it spontaneous. What will make it negative? Well, if it's already delta H is negative, and I'm going to subtract a negative number, I'm going to add to it. I want to make sure I don't add too much. I want to keep it negative. How do I make sure I don't add too much? I make sure my temperature stays low, okay? So there's going to be some low temperature that will allow it to be spontaneous. It won't happen at this temperature, but if you get it low enough, it will be spontaneous at this low temperature and every temperature below that. And a quick example of this is one that we've been examining, and that would be freezing an ice cube. You put it in the freezer, it happens spontaneously, right? That would be a negative delta G of the reaction. When it's freezing, it is pulling heat out of. That's an exothermic process. That water is sitting in the freezer is drawing the heat out and dumping it into the room. From the perspective of that ice cube, it is losing its heat. That's a exothermic. That's negative. Now the ice cube is going from a liquid state to a solid state. That is a decrease in the disorder. It's getting less disordered. Okay? So these are two negatives. Does it happen spontaneously on the counter in your bedroom? No. Does it happen spontaneously in the freezer where the temperature is low? Yes. So we have some reactions that are only going to be spontaneous at low temperatures. We got some reactions that are only going to be spontaneous at high temperatures. We got some reactions that will not be spontaneous in the forward direction at all, but only be spontaneous in the reverse direction. And we have some that are spontaneous completely. Now, how about this one here? If it's spontaneous as exothermic and getting more disordered, and we reverse the reaction, it's no longer exothermic but endothermic. It's no longer more disordered, it's less disordered. So can you see that we have just reversed the reaction? And so it's not going to be spontaneous in that way, but if you flip it around, it'll be spontaneous. So that is the connectivity between these thermodynamic terms that we've learned and this value, conceptually, not doing any calculations yet. But you could definitely use this equation to calculate the delta G for a reaction. It's not the easiest way to get it because you got to do a reaction, you got to do a calculation for this, you got to do a calculation for this, and then you got to add them together. And you're no better off than using the delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings with its two calculations and then adding them together. But it is a way of getting there. More often than not, is used to kind of track whether or not, just by looking at a reaction and knowing the signs of these guys, whether a reaction is spontaneous or not spontaneous. And if it's got conditional ways of being spontaneous, you'll be able to predict whether you needed to elevate the temperature or lower the temperature to get yourself there. All right, we answered that question already. All right, don't want to go to that one yet. We've got a predictor, second law of thermodynamics. We've got an equation that took that second law and gave us a new thermodynamic term. We'll see where we go next in our next lesson.